In this series, we are not just learning, we are mastering the art of understanding waves, starting from the basics and delving into the solved examples. It is like learning to surf, grasping the waves, feeling the movements, and finding your balance. So, together, let's ride these waves, navigate through challenges, and construct a solid foundation propelling you towards NEET success. Think of wave motion as a cool way energy travels through matter. It is like a dance party with the tiny particles in a material. They move back, forth, passing energy to each other like a chain reaction. This constant movement makes a disturbance, creating a wave that carries energy from one particle to the next. Imagine these particles as a dancer on a stage. They have grouped together. They create a ripple effect, transferring energy smoothly. This dance or wave motion happened in the material, turning it into the lively dance floor of energy exchange. So, wave motion is like as a dance of particles. A wave energy moves through material. It is not a still picture, but a dynamic, ongoing dance. Understanding this dance helps us to see how energy gracefully moves through the material. Let's talk about the different kinds of waves. There are three main types. First, mechanical wave produced in material with elasticity and inertia. Examples are water waves, sound waves, seismic waves. These waves needs a material to travel through. Electromagnetic waves does not need a material. They can travel through an empty space. Examples are radio waves, microwaves, gamma rays, etc. They are like invisible messengers, zipping through space, carrying energy. Third, matter waves are associated with tiny particles like electrons, protons, and other fundamental ones, creating a wave as they move. So, we have got waves that groove through materials, space, and even waves that follows the move of tiny particles. Waves are everywhere, showing off their unique styles. Imagine a ripple effect. It is a disturbance that travels through the crowd of particles. For the wave to propagate, the medium needs to be both stretchy, that is elastic, and resistance to change, that is inertia. Not everyone dances at the same time. Each particle starts grooving a bit later than its neighbor. The wave moves at a steady pace, but individual particles speed up in the middle and pause at the end of their motion. Energy passes between the particles like a secret handshake. Energy is transmitted through the wave. The individual particles remains in their place, undergoing vibration or oscillations without significant displacement. As the wave propagates, wave bounce off, bend around corners, mix together, and even create patterns in their movement. In this dance of waves, each characteristic adds a unique flavor to the rhythm, making it a mesmerizing performance of nature. Elasticity plays a crucial role in propagation of waves. Elasticity refers to the ability of a material to deform when subject to a force and return it into the original shape when the force is removed. Waves involve the periodic motion of a particle in a medium. Elasticity allows the particle to undergo deformation during this motion. When a disturbance, such as compression or a displacement, is introduced in the medium, elastic force acts to restore the particles to their equilibrium position. This restoring force is crucial for the oscillatory motion of particles, enabling the wave to travel through the medium. Inertia is defined as the resistance of an object to changes in its state of motion. For a particle or a segment of a medium, inertia reflects its tendency to maintain its current state of motion. Inertia plays a vital role in sustaining the motion initiated by elastic forces. When a particle is displaced from its equilibrium position, its inertia keeps it in motion until the restoring force brings it back to equilibrium. Inertia ensures that the particles continue oscillating about their mean positions, contributing to the continuous propagation of the wave. Let us unravel the dance of transverse waves, a symphony of crests and troughs. Picture a guitar string being plucked or the invisible dance of electromagnetic waves around us. Imagine the waves are hills, that is crest, and valleys, that is trough, in the landscape, creating the visual rhythm. To keep the dance going, there is a force that holds particles together called cohesion and a stretchiness in the medium called volume elasticity. Transverse waves exhibit lateral oscillations perpendicular to the distance of a particle displacement, resembling a propagating ripple across the spatial domain. These distinctive characteristics imparts a nuanced dynamism to the realm of wave phenomena, unveiling intricate patterns that renders the physical dance floor of physics profoundly captivating. Imagine each particle in a medium grooving back and forth along the same path. This is longitudinal wave motion. Picture sound waves making their way through liquids and gases, like a melody traveling through air. As the wave travels, it squeezes the particles together, that is compression, and then gives some breathing space, that is rarefaction. Visualize a spiral spring attached to a wall. As it moves, the coil dances in harmony, creating longitudinal waves along the spring's length. In the air, when the sound waves passes through, molecules in the certain region gets cozy, that is compression, while in between the regions they enjoy some space, that is rarefaction. As the wave travels, it introduces a dance move called the compressive strain. This dance is versatile, happening in solids, liquids and gases. The longitudinal waves brings the grooves to the world of waves, creating patterns and the movement that resonate through various mediums. Let's go through some basic definition related to waves. Wavelength, denoted by lambda, the distance traveled by a wave during which a particle of a medium complete one vibration is called a wavelength. It is also defined as the distance between any two nearest particles on the wave having same phase. Wavelength may also be defined as the distance between the two successive crests or troughs in transverse waves, or the distance between the two consecutive compressions or rarefaction in longitudinal waves. Time period, capital T, the time it takes for a wave to complete its trip over one wavelength. Frequency, denoted by N. This is defined as the number of waves produced in 1 second. If T represents the time required by a particle to complete one vibration, then it makes 1 upon T waves in 1 second. Therefore, frequency is a reciprocal of a time period, mathematically represented as N is equal to 1 upon T. Imagine it as the rhythm of song. Wavelength is the distance between beats. Time period is how long each beat lasts. And the frequency is how many beats you get in 1 second. Velocity of propagation is the wave speedometer, measuring the distance it cruises through a medium in just 1 second. Here is the magic formula that ties everything together. That is, V is equal to N into lambda. V is the velocity of wave, N is the frequency, and lambda is wavelength. The velocity of wave through string depends on the elasticity and inertia. Speed formula for a transverse waves on a stretch string is given by V is equal to under root of T upon mu. T is the tension in the string, mu is the mass per unit length. This too decides the wave's velocity. But here is the twist. Change the disturbance and you change the velocity and wavelength, but frequency is still loyal to the external source. In essence, it is a dance of tension and mass density, but the rhythm that is set by the external source. Navigating longitudinal waves through solid is given by V is equal to under root of Y upon rho. Y is Young's modulus and rho is density. Velocity of wave traveling through liquid is given by V is equal to under root of B upon rho. B is bulk modulus and rho is density. Wave through gases. Under constant temperature, density changes with pressure such that P upon rho remains constant. Equation for the velocity is given by V is equal to under root of gamma into P divided by rho. Now, density of water vapor is less than the density of air at same temperature. Hence, the speed of a sound increases with increase in humidity as per the equation. Now, let's work on some numerical problems together. But before we dive into that, I request you to leave a comment on the video. Your feedback is valuable, so feel free to share any suggestions or improvements you think would enhance the video and make it more useful for you. Your input is greatly appreciated. It is a question from AIPMT 2011 that involves the concept of change in wavelength as sound wave transition from one medium, that is warm air, to another, that is brass. The challenge is to calculate the wavelength of acoustic wave when it enters a brass from warm air. Velocity v is given as v is equal to n into lambda. N is the frequency, which is the property of the source of disturbance, and it remains same in air as well as in brass. Therefore, lambda is directly proportional to the wavelength. By taking the ratio of lambda in brass divided by lambda in air, we get velocity in brass divided by velocity in air. Substituting the values, we get 3500 divided by 350, which is equal to 10. Therefore, velocity increases by a factor of 10. Option B is correct. This problem involves a uniform rope hanging vertically with a block attached at the free end. A transverse pulse is produced at the lower end, and the wavelength at the lower end is lambda 1, while at upper end it is lambda 2. The task is to find out the ratio of lambda 2 to lambda 1. It is a question from NEET 2016 and relates to the concept of wave propagation and wavelength change in a rope due to different tensions. In our question, disturbance pulse is produced by external source, thus the frequency will remain same. Velocity and wavelength will change as wave progresses from lower end to upper end. Linear mass density will remain constant. Thus, therefore, V is directly proportional to under root of T. The T is tension. As the pulse travels up, for the pulse, tension in a rope goes on reducing from M1 plus M2 to M2. So, at the bottom the tension is M1 plus M2. Therefore, velocity V1 is proportional to under root of M1 plus M2. As the frequency n is constant, therefore, lambda 1 is proportional to under root of M1 plus M2. Similarly, when the pulse travels to the top, rope have only M2 as tension. Therefore, lambda 2 is directly proportional to under root of M2. By taking the ratio of lambda 2 to lambda 1, we get lambda 2 upon lambda 1 is equal to under root of M1 plus M2 divided by M2. Option A is correct. The given problem involves a string with a specific characteristics, length, mass, and tension. The task is to determine the speed of wave propagating on the string. This is a physics problem from AIPMT 1989 and is associated with the concept of wave velocity on a string under tension. Formula for the velocity is V is equal to under root of T upon mu, where mu is the linear mass density calculated as mu is equal to m upon L. On substituting the value of m and L, we get mu is equal to 0.035 upon 5.5. Substituting the value of mu and t in the equation for the velocity, we get v is equal to under root of 77 into 5.5 divided by 0.035. On simplifying it, we get V is equal to 110 meters per second. Option A is correct. The problem involves a stretch string with an initial tension that is later doubled. The task is to find out the ratio of the initial speed to the final speed of a transverse wave along the string. This question is from NEET 2022, is related to the relationship between the tension and wave speed. This question is from NEET 2022, is related to the relationship between the tension and wave speed in a straight string. V is given by formula V is equal to under root of T upon mu. Since mu has remained constant, therefore V is directly proportional to under root of T. Taking the ratio of V1 upon V2, we get V1 upon V2 is equal to under root of T1 upon T2. Since T2 is 2 times of T1, therefore V1 upon V2 is equal to 1 upon root 2. Option C is correct. The problem involves an ultrasonic scanner used in a hospital to locate tumors in tissue. The operating frequency of the scanner is given as 4.2 MHz and the speed of a sound in the tissue is 1.7 km per second. The task is to find the wavelength of the sound in the tissue. This question is from AIPMT 1995, is related with the relationship between the frequency, wavelength, and the speed of sound in a medium. Lambda is equal to V upon frequency n. Therefore, on substituting the values, we get lambda is equal to 1.7 into 10 raised to 3 divided by 4.2 into 10 raised to 6. On simplifying, we get option A as correct. The problem involves determining the wavelength of a wave based on its speed and the number of waves passing through a point in a given time. The speed of the wave is given as 760 meters per second and 3600 waves pass through a point in 2 minutes. The task is to find out the wavelength. This question is from AIPMT 1999, is related to the relationship between the speed, frequency, and wavelength of a wave, represented by the formula V is equal to n lambda. Number of waves passes in 1 second, that is the frequency, equal to 3600 divided by 120 is equal to 30 Hz. Wavelength of the wave is given as V upon n, that is velocity upon frequency. Substituting the value of V as 760 and n as 30 and simplifying it further, we get wavelength is equal to 25.3. Option B is correct. The problem is related to understanding the effect of humidity on sound waves. When humidity increases, it could be associated with the change in the speed or propagation of sound in air due to the variation in humidity levels. This question is from AIPMT 1995, may require a knowledge of how humidity influences the properties of the medium through which the sound wave travels. The velocity is also given by V is equal to under root of gamma P upon rho. Note, the density of water vapor is less than the density of air at same temperature. Hence, the speed of a sound increases with increase in humidity as per the equation. Option A is correct. I will advise you to visit www.gnet.com for concise notes and practice questions. In our next video, we will delve into the fascinating world of progressive wave phase, unraveling their equations and exploring the dynamics of velocity and intensity. Stay tuned for the journey from theory to solve numerical problems. Keep that focus sharp. Stay committed to your NEET preparation. This is Avinash, signing off. Thanks for being with us on this educational voyage. Before you go, don't forget to hit the like button, share this video, and subscribe to our channel. Until next time, happy learning.